Good day everyone, welcome back to our discussion on the topic differentiation. Today we'll be treating more example on the subtopic function of a function, also known as chain rule. Our first example states that if y equals to sine 2s, find dy ds. We know previously that the derivative of sine s is cos s, but in this case we are differentiating sine 2s. Now the idea is to make 2s to be equals to another variable. In this case we are going to be using z. So let z be equals to 2s, then the z over the s will be equals to 2, and y will be equals to sine z. That's y equals to sine 2s will be y equals to sine z. Now the y over the z will be equals to cos z, because the derivative of sine z will be cos z. Now from our chain rule, our formula is dy over the s is equals to dy over the z times the z over the s. Now substituting for dy over the z and the z over the s, it becomes cos z times 2, or 2 times cos z. At this point we are going to substitute for z, remembering that z is equals to 2s, and we are left with 2 cos 2s. Our second example states that if y equals to sine square s, find the z over the s. Y equals to sine square s is similar or the same as y equals to sine s in bracket square. At this point we are going to make our sine s to be equals to z, saying let z be equals to sine s, then the z over the s will be equals to cos s, because the derivative of sine s is cos s, and y equals to sine square s will be equals to z square. The y over the z will be equals to 2z. Using our chain rule, which states that dy over the s equals to dy over the z times the z over the s, we are going to be substituting for dy over the z and the z over the s. Substituting for dy over the z and the z over the s, it will becomes dy over the z is 2z. That's 2z times the z over the s is cos s. Multiplying, we will be left with 2z times cos s. At this point we are going to substitute for z, remembering that z is equals to sin s. Substituting z as sin s in our equation, it becomes 2 sin s cos s. And from our identity in trigonometry, we know that 2 sin a cos a is the same thing as sin 2a. So our 2 sin s cos s will be equals to sin 2s. Our next example states that evaluate d over the s in bracket e raised to the power 2s plus 3. Solution: d over the s of e raised to the power 2s plus 3 could be taken as y equals to e raised to the power 2s plus 3, find the y over the s, which means simply put we have to differentiate the function e raised to the power 2s plus 3. Our first step is to make our entire power to be equals to z. Let z be equals to 2s plus 3, then the z over the s will be equals to 2, and y equals to e raised to the power 2s plus 3 will be equals to y equals to e raised to the power z. Then the y over the z will be equals to e raised to the power z, because the derivative of e raised to the power s is e raised to the power s, so e raised to the power z will also be e raised to the power z. Now from our chain rule, dy over the s is equals to dy over the z times the z over the s. Substituting for dy over the z and the z over the s to be equals to dy over the z is e raised to the power z times the z over the s is 2. At this point we will be substituting z for 2s plus 3 back into our equation. Doing so, our equation becomes 2e raised to the power of 2s plus 3. We have another example from NECO 2003. It states that evaluate d over the s of cos in bracket 3s squared minus 2s, and we are given the option. Solution: let y be equals to cos in bracket 3s squared minus 2s. Our first step is to make our entire bracket to be equals to u. So letting u to be equals to 3s squared minus 2s, y will be equals to cos u. Now the u over the s will be equal to 6s minus 2, because differentiating 3s squared will be 2 times 3, which is 6, and moving on from the power we are left with s. Differentiating 2s to be 2, so 6s minus 2, and differentiating u with respect to y, the y over the u will be equals to minus sin u, because the derivative of cos u is minus sin u. When we are differentiating cos, it gives us negative sign. At this point, we are going to be substituting for the u over the s and the y over the u in our chain rule formula, which is dy over ds equals to dy over du times du over ds. Doing so, dy over du is minus sin u times du over ds, which is 6s minus 2. At this point, we substitute for u in our equation. U is equals to 3s squared minus 2s. Doing so, our equation becomes minus in bracket 6s minus 2 sine in bracket 3s squared minus 2s. The correct option is C. We have another example from NECO 2002. It states that if y equals to sine cube in bracket 4s plus 10, what is dy over ds? Our question also implies that y equals to in bracket sine in bracket 4s plus 10 close bracket all raised to the power of 3. Let u be equals to sine in bracket 4s plus 10, then y equals to u cube. We can easily get the y over the u, and the y over the u will be equals to 3u raised to the power of 2, or 3u squared, because 3 times 2 is 3, and 3 minus 1 will be 2. Now to get our du over ds, we are also going to be using chain rule or function of a function by making our bracket 4s plus 10 to be equals to z, and u will be equals to sine z. Next, we are going to find the z over the s, which will be equals to 4, and the u over the z will be equals to cos z. So you see in our equation, the u over the s will be equals to the u over the z times the z over the s, which is equals to the u over the z is cos z, and the z over the s is 4. Multiplying and substituting for z, cos z is equals to 4s plus 10, our equation will be equals to 4 cos in bracket 4s plus 10. Now we've gotten our dy over the u and our du over the s. Now to get dy over the s, also using chain rule, dy over the s will be equals to dy over the u times du over the s, which is equals to dy over the u is 3u squared times our du over the s, which is equals to 4 cos in bracket 4s plus 10. At this point, we are going to be substituting for u, recalling that u is equals to sine in bracket 4s plus 10, and doing so, our equation becomes 12 in bracket sine 4s plus 10 in bracket all square cos 4s plus 10 in bracket. Simplifying further, it becomes 12 sine square in bracket 4s plus 10 cos in bracket 4s plus 10. Our correct option is B. Our final example states that find the y over the s if y equals to log tan 2s to base e. In our solution, let u be equals to tan 2s, then y will be equals to log u to base e. The next step is to look for the y over the u and the u over the s. The y over the u will be equals to 1 over u. From our table, we know that log es is equals to 1 over s, so therefore log eu will be equals to 1 over u. Now to get the u over the s, we are going to be using chain rule, and we are going to be making z to be equals to 2s. If z is equals to 2s, then u will be equals to tan z. Our next step is to get the z over the s and the u over the z. The z over the s will be equals to 2, and the u over the z will be equals to sec square z from our derivative of trigonometric function. So from our chain rule, the u over the s will be equals to the u over the z times the z over the s. Substituting for the u over the z times the z over the s, the u over the z will be equals to sec square z, and the z over the s is equals to 2, so it will be equal to sec square z times 2. Multiplying this and substituting z to be equals to 2s, we are left with 2 sec square 2s. Now to get our dy over dx, we are also using chain rule. So dy over dx will be equal to dy over du times du over ds. dy over du is 1 over u, and du over ds is 2z square 2s. So substituting both of them, we are left with 1 over u times 2z square 2s. Substituting u to be equals to tan 2s, our equation becomes 2z square 2s divided by tan 2s. Thank you. We have some exercises for you to try your hands on. For more insight on this topic, you can check our Hidden Facts Further Mathematics textbook. You can get the hard copy, or if you are interested in the soft copy, you can get it at the website on the bottom of the screen. Thank you.